Welcome to the Consulting Specifying Engineer webcast. Can you specify CRAC systems to deliver free cooling in a data center? Sponsored by Data Air. I'm your moderator, Amara Razgas, and I'm happy to join you today on behalf of Consulting Specifying Engineer and CFE Media and Technology. Here are some tips and tricks to get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you are having technical problems with audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try. If you do need a technician, please type a message in the Ask a Question box and the tech team will get to you as quickly as possible. Individual user experience questions will be answered in the Answered Questions box. Type questions for the speakers in the Ask a Question box on the left side of your screen. The live Q&A session will start in about 45 minutes. Today's webcast is being recorded. You will receive an email within a week with a link to the on-demand event. To download a certificate of completion and a PDF copy of this presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. Now we will hear from the sponsor of today's webcast, Data Air. At the conclusion of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned after the video for today's presentation.
Why are more and more people choosing Data Air environmental control solutions? It's time to take a deeper look. For 5 decades, Data Air has been developing innovative answers for diverse customer needs, including the first computer room air conditioning system, first microprocessor alarm controller for computer rooms, first integrated humidifier, first variable speed air conditioning system and datacom, and first internet network communication for system controls and monitoring, honored with an AHR Innovation Award. For more and more users, with diverse challenges in critical environments, the solutions come together in one place, Data Air.
I'm happy to introduce today's presenters, Eric Jensen and Dan Mckinnis. As manager of the Applications Engineering team at Data Air, Dan Mckinnis oversees a team that reviews and modifies HVAC designs submitted to the company by specifying engineers. In addition, he approves, releases, and manages CAD drawings for mechanical, refrigeration, and piping. Dan received his Bachelor of Science in Mechanical Engineering and his Master of Science in Engineering Management from Cal Poly Pomona. Both degrees have served him well as he pursued a path in mechanical engineering, first working with cryogenic pumps and now with precision HVAC systems. Dan is a professional engineer and a member of ASHRAE, AHRI, and Tau Beta Pi. He sits on AHRI 1360 as a voting member and provides his input as to how computer room air conditioning units should be tested and rated for the Department of Energy to adopt into federal regulation. As General Manager and Vice President of Data Air, Eric Jensen's goal is to serve the project delivery process first and foremost. By understanding the drivers for each of the various stakeholders, Data Air can help achieve customers' goals. Eric seeks to build a strategic partnership versus inserting the company's products at a transactional level. In his role as National Sales Director for Data Air's parent company, Construction Specialties, for 11 years, Eric improved key account development from 10% to 30% and was instrumental in reorganizing the sales and product management teams across multiple business units for a collaborative and scalable sales approach. Eric takes great pride in people development. Thank you for joining us today, gentlemen. Let's begin.
Okay. Thank you very much, Amara, and I appreciate the opportunity to speak with everybody here today. As mentioned, we will be covering the One Wilshire story, which, for those who aren't aware, is the story of how an urban brownfield building was transitioned into a multi-tenant data center that, with state-of-the-art electrical and cooling infrastructure. We'll come to understand how the computer room air conditioning, forgive me, I think, okay, there we go. I think we're on the slide that we need to be on now. We'll come to understand how the computer room air conditioning solution that was presented was tailored to be site-specific and deliver free cooling year-round. Additionally, we'll cover how to specify an energy-efficient CRAC system without the use of a compressor. But first, I'd like to offer a shout-out to the team. Thank you to GI Partners, the building owner, Swanson Rink, the design engineering firm, and CoreSite, the building's largest tenant. So how do you transform a 50-year-old high-rise into that sits within the heart of one of America's largest cities to add state-of-the-art cooling and improve its overall energy efficiency? That's the challenge that One Wilshire was presented with. We'll discuss what those challenges were and the details of how they were overcome and what that ultimately delivered to the client. One Wilshire's an iconic building in many ways. It can't have service interruptions because of its essential role in mission-critical and life-critical services in Los Angeles and the Western United States, which I think all of us in the environment of that we're working in today can appreciate. So a couple of quick fun facts about the building. It was built in 1966. It's one of the first new high-rise buildings built in downtown LA after the height cap was lifted in 1958. It's 30 stories tall, 662,000 square feet, originally with 1,800 tons of cooling. It was a straightforward office building. That all changed in the 80s with the rise of the long-distance carriers. Once One Wilshire became a carrier hotel, that began with MCI having approached the building to set up a microwave antenna on top of the roof, which then in turn invited more carriers to join them in the building and connect with MCI and each other. Fast forward to 2013, when GI Partners paid $437 million for the building, which amounted to a record price per square foot, making it the most expensive commercial real estate that was out there. What they walked into at that time was kind of a jumble of unplanned power, cooling, and other infrastructure. Today, it's highly regarded as the most densely connected building in North America. It's developed directly atop North America's Western Fiber Hub. It's one of the top 3 telecom centers in the world. 1 in 3 bits of information that passes between Asia and North America passes through the undersea cable that terminates at the base of the building. So given that history of having been an office building through many years and slowly transitioning to a carrier hotel over a couple of decades, there were complexities and challenges, so a master plan really needed to be developed. Swanson Rink engineers took the lead on this. First, there was no available space. The primary challenge to effective solutions in data center type facilities is utilization of space. It's of utmost concern. And in this particular project, there was no bit of available floor space, roof space, shaft space, etc., interstitial or other. Everything was densely packed with fiber, communications cables, everything that builds up over the many years of converting to a carrier hotel. So space needed to be made. Not such a big deal in most projects, but a huge undertaking for an operating data center with multiple tenants. There was no central system. Without a building-wide solution for cooling and power, each tenant developed its own solution over the years, which used all the remaining space for power and unitary cooling risers. Needed a plan. The team developed a master plan and subsequent building upgrades that allow new tenants to take advantage of fiber connectivity, as well as Tier 3 mechanical and electrical infrastructure. In addition to the 30th floor roof, there's also a 4th floor low roof. That too, as you can tell from the various pictures that are on your slides, was fully taken up with the various tenants' infrastructure built up throughout the years. Cooling towers, air-cooled chillers, fluid coolers, air-cooled condensers, dry coolers, etc., all taking up all of the available footprint that was necessary in order to upgrade this facility to become 21st century ready. So this is really where the story begins today. The towers became a trade-off, the cooling towers, that is, became a trade-off between size, footprint, and efficiency. The key point that we're going to cover today in detail is the maximizing of the free cooling hours given a 67-degree supply water temperature. Swanson Rink went into this project looking at what was possible rather than looking at current solutions, and challenged the status quo in hopes that they wouldn't be limited in their vision. They sought a building-wide solution, a common cooling system for all the CRAC units in the building. The target was 50% free cooling. Now, Title 24 energy standards in Los Angeles and California would only require 70 hours of compressor-free cooling. The objective became 50%, so that was a pretty significant ask. They needed the ability to tap into a centralized system, so scalability was important. They utilized an elevator shaft through the removal of an elevator, because as more and more of the space turned from office into data center, there were fewer and fewer occupants throughout the years. So that was one of the clever ways that they were able to create new space for the infrastructure. They installed the condenser water piping throughout that shaft to serve this centralized cooling system. Now, as new tenants come online to that centralized system, they can tap in for their own benefit. Tier 3 for the Uptime Institute was the target. And so what really started as a logistics challenge of physical constraints and just-in-time deliveries became an energy efficiency story. So the ask and the solution. Now we're going to take a closer look at where data air became involved in the project, the equipment that was considered, the specific requirements laid out by Swanson Rink as the design engineer, and what eventually became the solution that was provided and installed, and what did that ultimately provide to the owner and the various tenants who come online. There were several alternatives across chiller plants or outside air economizers, but really the key driver was the space. And so a condenser water system became the best available option. With that, we're going to take a look at the specifics of how that system performed. There were several requirements specified by Swanson Rink for the equipment that was to be used as the centralized system. Every project, has its unique combination of whether it's location, building load, climate, etc. All those have to be taken into consideration to arrive at the best solution. With an ask of 72-degree supply air to the space, given the existing conditions of space limitation and the decision for a condenser water loop, a DX CRAC system that could provide dual cooling was the solution that was proposed back. They had what they believed were pretty lofty energy usage goals, and what we had to do is work through what ultimately that kind of a solution would be able to provide and how that compared to the 50% free cooling desire for the client. So Swanson Ring sent out requests for information. Data Air was a manufacturer who replied, and very willing to work through the challenges associated with everything that we've just laid out. So I'm going to turn things over now to Dan Mckinnis, who will be able to speak from his intimate knowledge throughout the project to how did our GeForce Ultra system meet the needs of One Wilshire and beyond. So with that, Dan?
Okay, thanks, Eric. Let's take a closer look then at the Data Air site-specific solution, which we put together to meet each of these goals. So the Swanson Ring team and Data Air team worked together to deliver a unit that exceeded the job requirements. So what we did was we started with the GeForce Ultra unit, like Eric mentioned, which has 2 cooling coils and utilizes a variable speed compressor operated by a VFD. So one of the coils is a refrigerant coil, and the other is an energy saver coil that uses water from the cooling tower to do compressorless cooling. So we optimized the water side coils, the valves, the condenser, and the internal piping to ensure a pressure drop across the entire unit of 20 feet or less, as well as ensure that the pressure drop between any of the modes of operation were nearly identical. So the goal being to have smooth transitions between the modes of operation. To eliminate bypassing any water, we changed the internal piping and software. We removed the globe valve and the bypass line that are typical in these kinds of CRAC units, and utilized a delay in the software instead to capture accurate water temperature on startup to determine the mode of operation to be in. So oversizing the chilled water coils and condensers, that was to provide the maximum free cooling hours and to minimize the pump horsepower. So now let's take a look inside the unit. So here's a photo here, and what that's showing in the red box there is the coils. So that's the energy saver coil, which is a 6-row coil. The 2-row DX coil is mounted behind it in a nested A-coil configuration. Down here is the EC plenum fans. These are the water regulating valves. Instead of using a single water regulating valve, we used 3 in parallel to allow for smaller internal piping as well as lower pressure drop and a smaller footprint. Here's the variable speed scroll compressor with the variable frequency drive actually right above it. And last, here's the hinged electrical panel that swings out of the way so that front access only is required for service and maintenance. So I talked a little bit about the 3 modes of operation. I'm going to go through those here. So the first mode of operation is the full DX mode. The second would be a compressor assist or supplement mode to energy saver. And the third is full energy saver mode. So this first mode that's shown here on this slide is the full DX mode. So in this piping diagram, on the left side of the screen, you're going to see the outdoor equipment. So this is the cooling tower and pump packages. And on the right side is the indoor equipment. So all of that would be in the CRAC unit. So if you follow the flow of water here, the water leaves the cooling tower through the pump package, comes into the CRAC unit. And the first thing it sees is this chilled water temperature sensor. So our controls are reading that temperature and determining which mode the unit should be in. So in this scenario, when the water temperature for this design, when it was above 74 degrees, we decided that to be the cutoff point where you would run compressor cooling, so full DX mode. So as you can see, the water is going to bypass that chilled water valve will be shut. It's going to go straight through the water regulating valves and into the condenser to cool the compressor, and then back around to the cooling tower to finish the loop there. The second mode, as I mentioned, this is the variable speed compressor assist mode. So this is basically when you can get some free cooling out of the water, but not enough to meet 100% load. So what you need here is the compressor to come on. And the nice thing about the variable speed compressor is that unlike a fixed speed where it would kick on all or nothing, it can come on and just kind of trim the difference that you need to maintain set point with very small changes in RPMs that it can adjust to match closely to the temperature set point. So again, here with this, I'll show you the water path. So as it goes from the cooling tower through the pump package into the unit, this time it's going to split. The sensor is going to, or the controller reading the water at the sensor is going to tell the water to split here, and it's going to go to the condenser as well as the energy saver coil. And I should mention, as the air comes into the unit, the air is going to hit the energy saver coil first before it gets to the DX coil. So you're always doing as much free cooling as possible, and the DX coil is just adding the difference there. So this was, if I didn't mention, this was the temperature range between 67 degrees and 74. As Eric mentioned, 67 was the design point to get full free cooling at. So that's our next mode here, the full energy saver mode. So that's when the water is 67 or below. And in this scenario, we don't need any compressors to operate. So we're able to do a full 100% load with the energy saver coil. So again, the water is going to come into the unit and go straight through the energy saver coil and then back to the cooling tower. And in this case, the water regulating valves will be shut because the compressors are not operating. So we've talked a lot about the economizer, but we can't forget the compressor. So the compressor needs to be as efficient as possible because it's going to operate thousands of hours a year depending on the conditions at the site. So this slide compares energy consumption of different types of compressors. And we need to draw a distinction between variable capacity compressors and variable speed compressors. So the digital scroll is a variable capacity compressor. It does a decent job of changing capacity to match the load, but it doesn't save much energy. Whereas a variable speed compressor saves a lot of energy at partial load. The red line at the top here shows the energy consumption of a digital scroll compressor at various loads. And as I mentioned, there's some energy savings, but not much. Whereas the green line is energy consumption of a variable speed compressor with a VFD. So the reason for the significant difference in energy consumption between these two technologies has to do with how they're modulating capacity. So the example in red, like I said, is a digital scroll compressor which engages and disengages the scroll set on and off to reduce capacity, but it keeps the motor spinning at full speed. The variable speed compressor with the VFD, it slows the motor down and takes advantage of the affinity laws, which define the relation in speed change in RPM to power consumption to the third power. So that may be kind of confusing, but to give you an example, if you reduce the motor speed from 100% to 70%, you only use about 35% of the power that you used at 100% speed. So what that is a 30% reduction in speed gives you a 65% reduction in input power. So that's a huge savings. So what happens though is the evaporator temperature will rise and the condensing temperature will fall, reducing the compressor lift required and increasing the efficiency. So that's effectively what's happening. In addition to the motor spinning much slower. So that's why you're getting such energy savings like that. So this part load efficiency is critical to this solution with energy saver. The compressor assist mode operates for such a large portion of the year with the compressor at reduced speeds to supplement the energy saver coils when the entering water temperature is above 67 degrees for this application. So that's why this is critical, and I wanted to go through that in detail. So here's a graphical presentation of the power consumption during the three modes of operation. So like I mentioned, when the water is at 67 degrees or below for this application, the green line shows that only the fans are running. So as you see, the water temperature on the x-axis and power consumption on the y. The green line is showing you basically just the fan energy usage during energy saver mode. Above 67 degrees, you'll see the blue line shows the compressor assist mode. And the power consumption increases a little because the compressor has now come on and it's operating at minimum speed and then ramping up with the water temperature. And finally, the DX only mode is when you hit 74 degrees and you no longer have economizer. So the orange line shows a big jump in power consumption if you're looking at the green as the basis. But if you look at it the other way around, the orange line is where you'd be operating year round with typical DX systems. And really the blue and green are just showing you to scale how much you're going to save for big portions of the year. And I'm going to get into that exactly how we determine how many hours of the year each of these operates. But first, let me show you how we did versus the One Wilshire goal. So as Eric mentioned, the goal was 50% of the year. But to help you understand what Title 24 is, so most states require some kind of economizer in every data room. And California is famous for having an aggressive energy code called Title 24. So what Title 24 requires is that you can economize at 100% load using airside economizer when it's equal to or less than 55 degrees outside, or with waterside economizer when it's equal to or less than 40 degrees outside. And because California, obviously, at least Southern California, doesn't get very cold, that works out for Los Angeles to be only 70 hours per year that you need a water economizer. So that's 70 hours per year that you're technically below 40 degrees ambient temperature. And 1,900 hours roughly for the airside economizer when you're below 55. So that's just to give you a baseline of what Title 24 would require for free cooling in Los Angeles. The One Wilshire goal was much more ambitious at 4,380, which is half of the year. But the data air solution on the right actually exceeded all of these. And the design, we were able to hit 6,200 hours with full economizer. So that's the 67 degree water that they were able to provide to the CRACs, and the CRACs were able to utilize to match 100% of the load. The other hours above that, the 25, 22, that's additional hours where we were able to do partial cooling in that compressor assist mode. So that's just an additional benefit on top of what the original requirement was. So the outcome was there were 3 modes of operations, like I mentioned, but this design in the end only really needed 2 modes as they were able to maintain the high side of the water at 74 or less. You would never need to go into that full DX mode. To see how that looks in days rather than hours might make it a little more clear. So 105 days a year, partial economization, 0 of standard DX cooling, like I mentioned, but 260 days a year of full economization. So that's compressorless operation. So you might say that's great, but this job's in Los Angeles and it has perfect weather. And you might be wondering, how will this work in other locations? So the data air solution depends on the difference between return air temperature to the CRAC unit and the outdoor wet bulb temperature. So if you look at other large cities, some that are much warmer, and you compare it to Los Angeles, the Los Angeles design conditions are 91 dry bulb and 70 wet bulb. But if you look at Atlanta, for example, the dry bulb design is 94 with the wet bulb of 74. Dallas, the dry bulb is 101 and the wet bulb 74. Phoenix, the dry bulb is 110, but the wet bulb is still 74. So if you're seeing a trend there, a lot of these cities that get much hotter in terms of dry bulb also have very low design wet bulb temperatures. So if you're using some type of evaporative cooling tower, you can still take advantage of this and get very similar results to what we saw in Los Angeles. So this project resulted in an annualized PUE estimate of 1.2. So if you're not familiar with PUE, it's power usage effectiveness. And to estimate PUE, you take the total facility energy consumption, which is the cooling plus the IT equipment, and you divide it by the IT equipment. So to give you an idea, a PUE of 2 is very high, but there are a lot of data centers operating at that level. More common data center PUEs is between 1.5 or 1.7. But the big takeaway here is that the full load PUE of this system is 1.2, and that's on a high-rise brownfield data center in the middle of Los Angeles with a building built in 1966, like Eric mentioned. So that's a very low PUE, and there are not many systems out there that really approach that number. So as I mentioned, we're going to talk a little bit about the number of hours that you'll see each of those modes of operation, but what's important to understand is this is far-reaching, not just in Los Angeles. It can be applied to many other places. So this next section is going to show you the efficiency numbers for other major cities where we've applied this site-optimized solution. So my first example here is Ashburn, Virginia, which is considered a national hub for data centers. And to calculate the energy usage and percentage of free cooling, we have to start with the bin data. So bin data is gathered from historical weather data for a particular location, and the number of hours that a certain location experiences temperatures within specified temperature ranges or bins is recorded. So here you can see on the table on the right, those temperature ranges are all 5-degree ranges, like 100 to 104, 95 to 99. Those are all 5-degree ranges. And the total OBS is the total number of observations in hours. So if you add up all those hours, you'll see 8760, it's a full year. But from that, we can now figure out how many hours this site is experiencing a certain temperature in that certain range, and we can do calculations on this with much more detail. So in addition, we also have the wet bulb temperature, which is also recorded for each of these bin ranges. So that's critical, again, because I mentioned if you're using an evaporative cooling solution for your cooling tower or fluid cooler, then you would need to know what that wet bulb temperature is. So looking at this, the first few columns here, I know there's a lot of data here. The first few columns are just that bin data brought into this table. So as you'll see, you have the low and high temperature ranges in columns 1 and 2, and then you have the wet bulb temperature and number of hours that this site experiences those temperatures. And what I did from there to get the entering water temperature, so this is basically the water leaving that evaporative fluid or cooling tower or a dry cooler. In this case, it was a cooling tower for this calculation. But what I did was I assumed a 10-degree approach. So that's saying that the water leaving the cooling tower can get to within 10 degrees of the ambient air temperature, wet bulb temperature. And that's a pretty common assumption to use. So that's what we did for this calculation. So you'll see those numbers are all 10 degrees higher. The compressor kilowatt in the next column, as you'll see, all the rows that are green are that fluid economizer mode. So the compressor kilowatt is 0. And when you go down into that blue section, you see the compressor assist mode. So the compressor is kicked on now at lower speeds. And then when you get into the orange, you're at the full DX mode and you're at typical compressor operation. The next column, evaporator fan kilowatts. This is just assumed to be constant throughout the year to make this a little more straightforward. And the total power is just combining those two columns. So the big takeaway from this, though, is figuring out what percentage of the year you can operate in each of these modes. So here, what you'll see for Ashburn, this same solution could operate 65% of the year in full economizer mode, about 10% in the compressor assist mode, and then 25% of the year, so a quarter of the year in full DX mode. That's with an evaporative cooling tower. If you decide to use a dry cooler, it's not much different. If you see on the right, the dry cooler approach for Ashburn was actually pretty good, 56% of the year in full economizer. So that's to give you an idea of how this would work there. This is the energy usage chart, similar to the one I showed previously, but just to give you an idea again. So Ashburn, 25% of the year up in that full DX mode, but the rest of the year you're down in the green and the blue modes. So pretty significant drop in energy usage. that you can get. Los Angeles, to show you the breakdown, because I know we've talked mainly about Los Angeles, but to show you how this breakdown worked out, as you'll see, everything below 35, it just has a dash because Los Angeles just doesn't get that cold. But what we were able to get out of Los Angeles is 72.8% of the year free cooling. But if you look at the compressor assist mode, we have almost the rest of the year. And as I mentioned, we found out later in the design, we actually didn't even need the full DX mode at all because they were able to keep the water temperature at 74 or less throughout even the highest points in the year. So there's a bigger discrepancy between the cooling tower free cooling hours versus the dry cooler in this scenario, because Los Angeles is fairly dry most of the time. So that's really the big difference. The drier the city is, the bigger difference you're going to have between cooling tower and dry cooler. So a few other examples here. This is that same chart I showed you, but this is nice to see now again because you can see that compressor assist mode is actually pretty wide for this solution. So that compressor will be running for about a quarter of the year in that compressor assist mode at that increased efficiency level. But if you look at Dallas, for example, so most people would think you couldn't apply this in Dallas, but you can actually get 40% of the year with the full economizer mode in Dallas using the same exact solution. And 53.5, including the full and partial economization. Next one here is Phoenix. So Phoenix, again, because it's very dry, big discrepancy between cooling tower and dry cooler, but you can still get, again, a huge amount of the year, over 50% with the free cooling and another 17 with the partial economization. And the last example I have here is Seattle. So Seattle, obviously, it's quite a bit cooler, but to show you that in the northern states and northern cities, you can get a huge percentage of the year in free cooling. So 83% of the year in this scenario. So that's all I have. I'll turn it back over to Eric.
Okay, thank you very much, Dan. Appreciate you running through those various scenarios as well as the details of the project design. Excuse me. So what I'd like to do at this point is just sum up some of the lessons that were learned throughout this effort. And really what we're talking about here is essentially everything that has already been stated, which is even an urban brownfield data center can rival that of a greenfield data center, as evidenced by this particular project having a 1.2 design PUE. Challenge the status quo. We encourage challenging of the status quo. Tried and true technologies, when combined with creative applications, creative uses, can really create innovative solutions for your clients. And as we just finished with, this solution has much broader reach, well beyond Los Angeles. Dan took us through a couple of specific examples that really represent a pretty wide swath of ASHRAE climate zones, whether it is, of course, Los Angeles having a temperate and dry climate, or Phoenix is hot and dry, and then you have Dallas is hot and humid, or Seattle is temperate and humid. So really a wide range of application for solutions that are based around or framed around what we covered as a specific example and case study here today. So with that, I thank you for your interest and your time. I'd like to turn it back over to Amara for any Q&A.
All right, excellent. Thank you so much for that information and those terrific examples. Now, Eric and Dan will answer questions from the audience. Please type your questions for the presenters in the Ask a Question box on your screen, and we'll get to as many questions as time allows. Questions that we do not get to today will be posted online at www.csemag.com. And please remember to download a certificate of completion or a copy of this presentation. Use the Event Resources tab on the left side of your screen. All right, gentlemen, let's take a few questions. Dan, I'm going to start with you. So this is kind of a general question, Dan. What are the standard options you'll be providing? Can you provide a little bit of information on that topic?
Sure, yeah. So, I mean, CRAC manufacturers should be fully equipped to offer cooling, humidification, dehumidification, as well as other various sensor controls and monitoring.
All right, got it. Thank you. Dan, looks like you are the winner here. You get the next question as well. Please elaborate on the topic of non-compressor solutions. Can you discuss outdoor air quality issues as it relates to airside economizing? Can you talk about that a little bit, please?
Sure. So airside economization can work well in some environments, but typically waterside economization is preferred in data centers to airside economization. One reason is to avoid introducing outside air and any airborne debris into the data center, and another is due to the data center location within a building, and it may not be ideal to have long duct runs being needed to pull air from the outside into the data center.
Okay, very good, got it. And Dan, one more question for you right off the bat. What are some benchmarks for data center energy usage per square foot per year, or is there some other metric, or can you give us kind of a broad picture of how to calculate this?
So to know kilowatts per square foot, it's going to depend a lot on the layout, but a typical metric that's used, or at least design criteria, is around 4 to 6 kilowatts per rack. While obviously high density racks can go much higher than that. But a common metric that's used for the energy efficiency in data centers is something that I discussed already, which is the PUE, the power usage effectiveness. And as I stated earlier, the PUE's range, a typical range, is between 1.2 and 2.0. The lower the number being higher efficiency.
All right, excellent, thank you. Eric, this next question goes to you. Can you please provide information on the project cost and duration and impact on annual PUE, power usage effectiveness?
Sure. So the PUE for this particular case study was discussed, of course. It turned out to be a design PUE of 1.2. The project duration was roughly 2 years of programming and design, as far as I understand it. We got involved through the design process, so I don't necessarily have a firm date on when programming began with the client, GI Partners. And then there were another roughly 9 months or so until the first tenant to come online with the centralized system was really fully online. So that was roughly 2 years programming design plus 9 months of call it construction and commissioning. So we're not necessarily privy to all of the costs, being an equipment provider. However, obviously it's related to the efficiency that was realized. There were some additional efforts that were spent optimizing the hours of free cooling. If the question is really intended to ask kind of maybe a trade-off, what is the balance between the design energy spent in versus what you're able to save on the back end. So of course that's always a balance that needs to be struck by the team. I can tell you that there was not a tremendous amount of back and forth just tinkering with the design. Swanson Rink kept very much on task with that, I would say, from our perspective. as the project was delivered on time. Maybe one other comment that helps to try to answer that question, though, would be that the simple payback on the solution was well under 3 years.
Okay, good to know. Thank you. And as a reminder to our audience, if you'd like to ask a question of either Eric or Dan, you can type the question into the Ask a Question box on your screen. You may type their name before the question, and we'll get to as many questions as time allows. If there's something that we don't get to today or something that requires a great deal of information, we will answer it in the online version of the Q&A that goes with the archived portion of this webcast. Okay, Dan, another question for you. Alterations and considerations for installing new CRAC units in existing rooms. Can you outline those options?
Sure. I mean, the big thing to take into account with older data centers or old data rooms is containment. So airflow management is something that's become much more widely known and accepted recently, but older data centers may not have much containment or much in terms of airflow management. So that's a big consideration. And another thing is to consider how equipment will be brought into the space, which can sometimes be a challenge.
All right.
Yeah, I'd just like to add the other, if I can just add, the other thing to take into consideration, of course, is service access. What are the points of service access, and what might be your options, for example, for front access only or things of that nature? Those are all answers that your CRAC provider ought to be able to offer to you.
Sure, makes sense. All right, thank you, Eric and Dan. Let's see, Dan, the next question's for you. What are the typical requirements for cooling data centers? That's a very broad question, so if you can tackle that in 3 seconds or less, that would be awesome. I'm kidding. Take your time.
3 seconds. So it is a broad question, so I think the best way to answer would be to reference the standards. So there's a few governing bodies out there that have control of data rooms. ASHRAE TC 9.9, which is mission critical facilities for data centers, technology spaces, and electronic equipment. So it's published its guidelines, and which recently led into a new standard being developed, which is ASHRAE 90.4, which is the energy standard for data centers specifically. Very similar to ASHRAE 90.1, if you're familiar with that, but just specific to data centers now. In addition, AHRI 1360 plays a role in establishing rating conditions for CRAC equipment, while ASHRAE 127 handles method of test. And the Department of Energy has worked with both ASHRAE and AHRI committees and has adopted minimum efficiency requirements measured in SCOP, which is Sensible Coefficient of Performance. So I know that was quite a bit. If you have any follow-up questions or want that written out, please feel free to contact us after and we can get that to you.
Sure, exactly. If you do have additional questions or if you need more information about those basic codes and standards, feel free to type your question into the Ask a Question box on your screen, and those questions will be answered in the on-demand portion of the webcast. That is all included on the website. All right, Dan, the next question's for you again. Can you please discuss the economics a little bit? So paybacks will be lower in California due to the higher electric rates, but in areas where electric rates are lower, paybacks might be more attractive. Can you talk about that?
So you're saying, well, it says in areas where rates are lower, paybacks might not be as attractive. So that's true, but my thought on that would be that the additional investment to add the economization solution to this wasn't too large. So you would still have a good payback in many other locations. What we're able to do is utilize that condenser water for the energy saver. So it wasn't like they had to modify the entire condenser water system just for us. We kind of worked around that. So to summarize, I guess the additional investment for making this economization work wasn't a big difference in the entire scope of the project. Eric, anything to add to that one? I know that was kind of similar to the question you just answered.
I don't, but I think what we could do is maybe solicit for any follow-up questions outside of this on that topic.
Okay. Well, Eric, you get the next question. So the audience member understands about minimizing airside economization, but did or does the building have outside air associated with it for ventilation or pressurization? Can you please outline that?
So I can only speak to the entire building on kind of a limited basis. However, outside air economization was pretty quickly dismissed for this particular project for a couple of reasons. One is Los Angeles air quality. We live near Los Angeles, so I can appreciate that. But beyond that, we really talked about how densely packed the building was. And it would take a substantial amount of layout in order to get all of the ducting configured to make that solution viable for this particular scenario. But as for whether there is any additional pressurization, I'm not aware of any. Certainly there isn't anything on the ventilation side for airside economization.
Okay, sounds good. Dan, this next question goes to you. What are the pros and cons of different modes of supplying cool air to the racks? And we're talking about a couple different options here. We're talking about raised floor distribution, overhead distribution, and in-rack cooling. Can you please describe?
Sure. So if you're laying out a data center from scratch, obviously you have a lot more options. I would believe the preferred method would be the raised floor distribution, and that's because supplying the cold air low through the floor, you get to take advantage of the natural convection as it comes out through the tiles, up through the racks, and then rises up to the return and the stratification. So that would be the preferred option just for that reason. The other methods from the top wouldn't be a bad scenario, and a lot of times just based on the existing layout of a space, you might have to go with that route. And the in-row cooling versus the perimeter cooling, typically we see in-row cooling units used when you have really long rows or trouble getting air all the way to the middle of a row, so you put that in to reduce like any hot spots. But yeah, like I mentioned, I think if you were laying it out from scratch, you'd prefer the perimeter cooling and the underfloor distribution of air. That'd be the best method.
Okay. Let's see here. We have time for probably one more question, depending on how quickly you go here. So let's see, Dan, let's talk about climates. For northern climates, do you assume a glycol solution in the core water loop? And did that affect efficiency? You had a couple different examples, so perhaps you can use one of those examples for your response.
So yeah, glycol will affect efficiency a little bit, but because it's so much colder, typically you're still going to get a big percentage of the year with free cooling. So you get less out of the fluid, but it's colder out for longer in the year, so you can actually still do quite a bit of free cooling. So it may not have as big of an impact as you would think.
All right, excellent. Thanks for that quick response. And we do now have time for one last question. And Dan, I'm sending this over to you. What is the energy penalty for the additional cooling coil within the CRAC unit?
I don't have that number off the top of my head, but that is a good thing to consider. I can definitely follow up on that if somebody's looking for very specific answer to that one.
Okay, excellent.
But it is worth noting that it was taken into consideration for this particular project and incorporated into the results that were presented.
Excellent, got it. We will make note of that question. I'd like to thank the audience for some terrific questions, and thank you again to the speakers, Dan Mckinnis and Eric Jensen, for sharing their time and expertise. I'd also like to extend a special thank you to the sponsor, Data Air, for sponsoring today's event. Now that we are just about done, we want to hear about how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve these webcasts. Finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, I'd like to thank you for attending. This is now the end of the webcast. Thank you and goodbye.